Okay, so here we have the 11.2 paper 1 questions. So power generation and transmission. So the examiner's report says that this question was challenging, but it's challenging if you don't realize the connection between RMS value and direct current value. And it's kind of the entire point of taking RMS value. Not only does it solve the problem of when you take the average of the min and max on a sine curve, you get 0. It also approximates the DC equivalent of that alternating current signal. So if it says the direct current is I, and it's like, what's the RMS value that dissipates the same average power? That RMS value would also be I, choice C. Because the RMS value of the alternating current is, again, the equivalent of the direct current value. So they're the same thing. I think that's what they're getting at. So if you look at it that way, it's actually a pretty easy question. But if you don't see that, maybe you're kind of just lost in the woods because you don't know how to approach it. Whatever. Next question. And here we have ourselves a diode bridge where the output is DC and input is AC. So, looks like a pretty well set up voltage divider. Everything seems legit. So the answer is going to be full wave rectified current because that's what did I say voltage divider? I meant to say diode bridge. That's what a full diode bridge will give you. So the answer is A. But wait, no, the answer is D. Why is it D? Let's actually trace the positive and negative voltages to see what is going on. So it really doesn't matter which side you make positive, which side you make negative. Let's trace. Alright, so positive terminal goes around, la la la. It stops because the direction of the diodes is for positive flow, so it's going to stop there. It's going to go through this guy and to this terminal of the output voltage. Yippee. Now let's trace negative. So it comes around here, la la la, comes around here, and then it stops right here, and it goes through there. No, it doesn't. Remember that diodes, the way they're drawn, the way they're biased, I think they call it, is for positive voltage. So here I'm dealing with the negative, so it actually does not go through this diode here. It stops right there. And it actually goes through this diode here. But wait a minute. I already have this bottom terminal is already the positive terminal. And now I have nothing going to the other terminal, the top terminal. So there's no actual connection. I have no current. That's why the answer is D. Now I could fix this. If I wanted to fix this and actually get an output full rectified current, I'd have to flip this guy around, I'd have to flip this guy around. But if I wanted to fix it. So 2 is D. Alright, next question. Okay, so number 3, transformers. In order for your transformer to work, how does it work? Electrical connection between primary and secondary coils. Now, the coils don't actually touch. It's an induction thing, right? Because of Faraday's law and Lenz's law. So there's actually an insulator between the coils so that they do not touch. So electrical connection between them, no. So no, not that, and not that. So it's B or D. And it would need to be B, an input of alternating current, because in order to induce a current, Faraday's law requires a change in flux per unit time. So alternating current would create that change in flux. The direct current would, when you turn it on, would have an increase in flux because it's an increase in current. But then once that current starts flowing and there's no actual change in current, there's no change in flux, so there's no induced current in the secondary coil. So that is a negative. That's not going to work. 3 is B. Number 4. Oh, look at this. We have another diode bridge. When I first saw diode bridges, I thought they were ridiculously confusing, but now that I understand how they work, I actually think they're kind of cool. But nobody actually cares what I think about diode bridges. Let's just answer the question. Okay, so before it says the conventional current, the current that is in the load resistor. What is true about it? Well, let's do a trace of the output, just to do it because it's good to do. So here's the voltage breakdown when positive is on the top terminal for the alternating current, and when positive's on the bottom. But in either of those cases, again, this is how the diode bridge works. You can see that for the load, positives on the right and negatives on the left. Charge flows from positive to negative. So that red arrow, the flow moving to the left, is going to be the direction of the direct current as a result of this rectification, no matter what the terminals are in the alternating current. So then, even though it's direct current flowing from one point to the other, it is not from P to Q, it's from Q to P, so it's not choice D. And then the answer would be choice C, zero average value during one oscillation. That would be true. Oh, one oscillation. I do 2 cycles. And so zero average value during one oscillation, that would be true if it were not rectified, but that's the entire point of a full rectification circuit. So it is not C. And then it says A is a maximum twice during one oscillation of the input voltage. That would be true, and because when we fully rectify the signal, we flip the negative voltage to become a positive voltage. So that's actually the signal that's going to occur with no negative values. And so yes, it achieves a maximum value twice in the cycle. Now it says, B says is never zero. It is zero at 3 points in the cycle for an instant in time. So it's not that it's never zero. So not B, but it is A. We're good to go. Alright, so first of all, we have an ideal transformer, and it's asking about the power transfer. If it's an ideal transformer, there are no power losses in the transfer. So if it was 20 watts to start, it's 20 watts to finish. But the ratio of primary to secondary and the number of coils is the inverse of the ratio of the currents. And they don't give the two currents, but they do give a voltage. So using the power and the RMS voltage, I'm able to get that the current, RMS current, is 2/5 of an amp. And it said that the RMS current in the primary coil is 2 amps. So 2 over 5 over 2 is 1 over 5. So the ratio of the primary coils to the secondary coils is 1 over 5. That gives us choice C. Okay, so for number 6, we have to read carefully. It says resistor designed for use in a direct current circuit. And then it talks about how it's actually being attached to an alternating current power supply with a peak potential difference of 10 volts. That's V naught. And so if we're working with a direct current equivalent resistor, what we want is VRMS. So if we find the RMS value, that's going to be like the DC equivalent. So if VRMS is V naught over radical 2, so 10 over radical 2 winds up being like 7.07 volts. And you might say, oh, well, the resistor says 50 watts, so the power dissipated would be 50 watts. Yeah, if it was attached to a direct current source, which it's not. So it's not 50 watts. And so we can actually, using the RMS voltage, we can figure out the actual power that was dissipated. And so the actual power dissipated in the circuit is 25 watts. It's actually 30 watts because it's one significant figure, because they said 2 ohms, one significant figure, but whatever, we'll let it pass. So 25 watts is our answer for what was actually dissipated, and that's A. Okay, number 7. So we have a sine curve for an alternating current. We have peak current is 2 amps, and it wants the average power dissipated in the resistor, and the resistor is 4 ohms. Well, again, if you take the average of the peak currents of 2 and negative 2, you get 0. And so the average 0 times 4, or 0 squared times 4 is 0, so the answer is 0. Clearly not. 0 is not an answer choice. So when we talk about average, we're not averaging the peaks. Remember that the way we handle average for these sine curves is root mean square. So what we're going to need is the root mean square current from this graph. And so that would be about 1.4 amps. And we're looking for the power dissipated in the resistor. Now we know the RMS current. And so we do P is I squared R. And voila, we have an average power of 8 watts, 8 watts, which is B. All right, next. Number 8, we just talked about this in class yesterday. Yesterday? Doesn't matter. We just talked about it in class. Why are high voltages and low currents used when electricity is transmitted over long distances? And basically, you want to minimize your heat losses. Those are sometimes referred to as I squared R losses. The resistance, of course, is dependent upon the properties of the conductor. So you could have high voltage or low voltage, high current or low current. That's not going to affect the resistance of the conductor. So high voltages is not going to affect the resistance. Never mind that V and R are directly proportional anyway. So it's not that, but rather you want to minimize the energy losses. You want to minimize your heat losses. That's what I said. That's the answer is C. Has nothing to do with the drift speed, and cables can be closer to the ground. I don't even really know what that means. Like, I think they just kind of made up that answer. Yeah, we want to reduce energy losses by having, one other point. How is reducing energy losses, what does that have to do with high voltage, low current? It's the current causes heat. That's the thing that's actually causing the heat in the wire. The more charge flow you have in there, the hotter it gets because of the collisions between the charges and the structure of the conductor. So by reducing the current, that's how we reduce the energy. We're not reducing the power per se because P is VI. So by bumping up V, we reduce the current, and that's how that works. You can see that I'm not lying because the mark scheme says the answer is C. C for the mark scheme. So for that right there. No comment from the examiners. We'll poo on you. All right, number 9. All right, so power P is dissipated in a resistor R when there's current I in a resistor for direct current. This is what's the average power dissipation in a resistance of half that value when the alternating root mean square RMS current is 2I. So we don't need to really make any adjustments because the RMS current is in line with average power. So really we're just kind of doing P equals I squared R again, but we have half the resistance, but double the current. And so, of course, I is squared, so that would be 4 times, and half of 4 proportionally is 2. So we would have double the power, and that is B. Okay, we have ourselves a diode bridge constructed as shown, and we have statements about the diode. So when diode P conducts, Q does not conduct. And yeah, I could see that as true. Ignoring the negative voltage for a moment, just tracking positive for now in terms of tracking the charge flow. So let's start with M being positive. So there's our path for the charge flow, and we are stopped at P, so P is not conducting and Q is. Now if I flip that around and I make N positive, one other thing, I wanted to point out that the direction of the current flow is to the left in that instance. Now I'm going to erase everything that I did except for the current flow through the load, because I want to show you that the current flow is going to be the same because of this diode bridge situation. But I'm now making N to be positive. So tracking that across, we start from N, La, la, oop, nope, stop. La, la, la. Oh, nope, stop. Oop, through the load. And oh, through P and back, and yep, back to M. So it doesn't matter if M is positive or if N is positive, we still have a leftward current flow through that load. Now it says when P is conducting, Q is not conducting. That is true. Then it says too, when S conducts, neither P nor R conducts. Well, let's do a trace for that. All right, so I want to be going through S. So if I start from M, I come down, I get stopped at P, I go through Q, I go through the load, I get stopped at R, I go through S, so S is conducting, and I go back to N. Now it says when S is conducting, neither P nor R conducts. Yes, that is true. When S is conducting, P and R are blocking that positive charge flow. But then number 3 says the direction of conventional current in resistor is from left to right. No, we've established it is flowing to the left from right to left, so that is not true. So 1 and 2 only, that would be A, the end. All right, next question. Is it just me or are diode bridges awesome? Although I don't like when they have this like kind of crossover situation like that. I find that confusing, but whatever. Okay, so we have a diode bridge. It says, what's the variation with time of the output voltage? This is a full diode bridge, so it's going to be a full rectification, so it's not C or D. That would be a half rectification. And so let's see. It has a time period of 20 milliseconds. It says that in the description. So that means that the full cycle is completing in 20 milliseconds. Let's remember what a fully rectifying circuit does. It takes the negative portion of the voltage and flips it into the positive. So the full cycle is going to need 2 peaks. So again, just to be clear, that's what's actually happening with the alternating current, but what a full rectification circuit does is it takes the negative portion of that current and it turns it positive, makes 2 peaks, but that's in one cycle. So one full cycle is going to need 2 peaks, not 1 peak. B has 1 peak for 20 milliseconds, that is NG. The answer is A, because it has 2 peaks in 20 milliseconds. Okay, number 12, transformer, 600 turns in the primary coil, so we have N primary is 600, and used to charge change an alternating root mean square potential difference of 240 volts RMS to 12 volts RMS. So the ratio, all right, so number 12, it gives us the number of turns in the transformer. It gives us the both the primary and secondary voltages, potential differences, or EMFs, whatever, they're calling them the same thing. It doesn't really matter that they're both RMS, it's just a ratio of 240 to 12, so that's a ratio of 20. But what actually gets produced when you do, we have a 120 watt 12 volt lamp. If we figure out the current in that lamp, that's 10 amps worth of current. And it says that the current in the primary coil is 0.6. If you do the ratio of secondary current to primary current, we get 16.67, 16 and 2/3. The original ratio of the voltages was 20. So there is a loss there. If it was an ideal transformer, that ratio would be the same, would also be 20, but it's not. There's a loss. And so the efficiency, if I do the 16 and 2/3 divided by 20, I wind up with an 83% efficiency. So not 99% efficiency, but 83% efficiency. And then if I figure out the number of turns, just looking at the original potential differences of that ratio of 20, I can do the ratio of the voltages is the ratio of the coils, which is equal to 20. And so we have 600 turns in the original, in the primary coil, so then that means that the secondary coil is going to be 600 divided by 20, or 30 turns in that coil. So NS is equal to 30, And there's our answer. And then you can say, well, what about the other ratio? What about the ratio of the currents? Well, if I use the ratio of the currents, I wind up with 36 turns, and 36 is not a choice. So I'm supposed to be using the voltages, not the currents. Okay, so we have power generated from an AC generator, and it says if you decrease the frequency, so if frequency, we know that frequency and period are inversely proportional, so if frequency goes down, then the period is going to go up. And so I can see that the peak output power, and this power is related to the voltage, so there's both positive voltage and negative voltage. I can see that that would be one cycle right there in 2 seconds, and so I want my cycle the period's going to go up. So I don't want a cycle of 2 seconds. I want a cycle of 4 seconds. So it's not going to be A or B. I want to have a period of more than 2 seconds. In this case, I guess 4 seconds is my choice, but both C and D are potential answer choices if I'm only looking at the effective frequency on period. But let's remember Faraday's law that is dependent on the rate of change of flux. If I have a lower frequency, then my rate of change of flux is also going to decrease. I'm going to be cutting those field lines less frequently. And so if I have a lowered rate of change of flux, that is going to lower my the voltage produced. It's going to lower the power produced, so my output power is going to decrease. So not only is my period going to increase, but the output power is going to decrease because of Faraday's law. That gives us C. Number 14. So they give us the current. We have a transformer. It gives us the turns in the primary coil is NP, secondary is NS. One coil has 1,000 times more turns than the other coil. So really what that means, 1,000 times the other, I guess it doesn't say which is which, but the ratio of the two is like NP over NS or NS over NP is 1,000. And then it's like, well, which is it? Is it 1 over 1,000 or is it just 1,000 over 1? Well, we do know something about the current. We know that we have a milliamp in the primary coil. And so if the ratio of primary to secondary in the coils is simply 1,000, then the current in the secondary coil is going to be 1 amp. And so the answer could be choice B. Alternatively, if the ratio is 1 over 1,000, so it's like the answer could be choice B. It's not choice B, and I'll show you why, and it's really kind of a dirty reason why. But I'll say B, B. Obviously, the mark scheme says the answer is A. The answer is A, but I'm going to get into why. Let's consider the alternative that if the ratio of primary to secondary is 1 over 1,000, and I put in 1 milliamp for the primary current, that gets me a secondary current of a microamp, 1.0 times 10 to the negative 6 amps. So in that case, the answer is A. A, which is it? So if we actually go back to the question, it says a current of 1 times 10 to the negative 3 amps flows in the primary coil of a step-up transformer. Step-up transformer. A step-up transformer means you have a step up in voltage. In order to have the power be maintained, be conserved, if my voltage is increasing, then my current is decreasing because P equals VI. P equals VI, right? So for the same P, if V goes up, then the current goes down. And so the secondary coil current is going to be less than the current in the primary coil. And so if the current in the primary coil is a milliamp, then I don't want an amp in the secondary coil, I want a microamp. The answer is choice A, not choice B. So you had to see that point about the step-up transformer. Sneaky, sneaky. Next question. Alrighty, so knowing the number of turns in the first and second coils, we get a ratio of 0.5. That means let's remembering that N1 over N2 is voltage 1 over voltage 2. That must mean if N1 over N2 is 0.5, that must mean that the second voltage is greater than the first voltage. This is a step up transformer. And considering that the power is going to be roughly the same, or in an ideal transformer will be the same, if I have an increase in voltage, there's going to be a decrease in current. So the max current is not going to be in the secondary coil, it's not going to be more than the original, so it is not A and it is not C. But now what's interesting here is let's take a look at the phase change. The answer is D, and there's a 90-degree phase change. Now why is that? Let's remember that EMF, because what transformers do is they induce a voltage and therefore a current from the primary coil to the secondary coil, but you get the most induction when you get the greatest change in flux. And you're going to get the greatest change in flux when there is the greatest current change. In other words, where the greatest voltage change and the greatest current change. The voltage graph and current graph look the same. That's because voltage and current are directly proportional, so however the voltage is changing, the current is changing with it. Now, if we see in the beginning that we have the maximum slope value at time 0, that's going to be the greatest change in current. It's also going to give us the greatest change in flux. And if there's the greatest change in flux, that's going to induce the most voltage in the secondary coil. So if I'm getting the greatest change in flux at time 0, I'm not getting 0 current at time 0. I'm getting max current at time 0. So my answer is D. All right, next question, 16. Oh boy, look at these. 16 actually gets into the use of a capacitor. This might actually be an 11.3. Why is my pen not working? An 11.3 question because you haven't seen capacitors yet. But and it says we want the most smooth output signal. If you want a smooth output signal, you have to include a capacitor in addition to the load. So I don't want another resistor. I want to include a capacitor. Now, do you include the capacitor in series or do you include it in parallel? Now, as for the capacitor, so what happens with a capacitor is a capacitor is like a bucket that you can fill up, can develop a voltage across, and eventually the voltage will release over time. I use the example of a bucket. It's kind of like a charge bucket. It stores up electrical charge. So our answer is going to be C, and I can tell you why it's not D. Because D is like, well, D includes the as the load and the capacitor. Here's our capacitor. But the problem with that is that there's going to be no current flow while you're waiting for the capacitor to reload, to recharge. Whereas for C, while you're waiting for the capacitor to recharge, there will still be current flow through the resistor in parallel beside it. And so now it's to produce the most smooth output signal. And so basically, without the capacitor there, you wind up with, like, say, no capacitor. You're going to get a graph that looks like that. But with the capacitor, it smooths it out. It kind of goes like up and then up. It never actually goes down to 0, so you're getting much closer to a steady value. And the reason why it doesn't go down to 0 is because that capacitor is storing electrical charge. It's kind of storing potential in it. And so while the voltage dips to zero as the AC power source cycles without the capacitor, like dipping to zero, like 0, 0, 0, 0. When you have the capacitor, that capacitor stores the voltage periodically, and so it does dip, but it doesn't get down to zero. So it basically smooths, where this is kind of like we're getting rid of the negative voltage with a full wave rectifier, but it's still dropping to zero. When you include a capacitor, it never really does that and gets closer to a direct current, a DC signal. And so that winds up being C. And again, it's like, well, you just mentioned what the capacitor does. Why can't the capacitor be in series? Why must it be in parallel? Because if the capacitor is in series with the load, there will be no current flow while the capacitor is waiting to charge. So that energy is going into the capacitor, and like when the capacitor releases, then there will be a current flow. But while the capacitor is loading, there's a break in the circuit essentially, and you get no current flow. Whereas if you wire the resistor and the capacitor in parallel with each other, while the capacitor is loading, you still have a complete circuit because there is a load in parallel with it. So you wind up with C being the legit setup and not D. You want your capacitor in parallel with your load, not in series with it. Okay, number 17. We have power versus time. What's the frequency of the power supply and what's the power in the resistor? And of course, we're going to get two power in a full cycle. We're going to get two power spikes in one complete cycle. So here's our period, 0.04 seconds. And so frequency is 1 over the period. So 1 over 0.04, we get a frequency of 25 hertz, not 50 hertz. So it's either A or C. And so we do not have a scaled y-axis, power axis on that graph, but we do know that our resistor is 100 ohms and our RMS voltage is 60 volts. And so average power, and what's average power? So average power is V squared, V RMS squared over R. And so that is 60 squared over 100, which is 36 watts, giving us choice A. Okay, 18. So for a perfect transformer, 100% efficient, the number of turns for the primary coil as opposed to the secondary coil should be the inverse of the current in the secondary coil over the current in the primary coil. But it's asking for the efficiency, and it actually gives the ratio of primary to secondary is 2.5, and it gives the two currents, the secondary to the secondary current is 0.5 amps, and then the primary coil is 0.25 amps, and that winds up being 2. So the original ratio is 2.5, but the actual currents, the ratio of the actual currents that are produced in the transformers is 2. So if it was 100% efficient, that would also be 2.5. So we are not 100% efficient. And in fact, 2 over 2.5 is 80%, and that's our answer, choice C. You can see that right here. The mark scheme says C. C. All right. Okay. I just like playing with PDFs and vector-based fonts. All right, 19. All right, so we have a generator making peak EMF E0 and periodic time T. When you double the frequency, what happens to the EMF and what happens to the periodic time? In other words, the period. So if I increase the frequency, I know that we decrease the period. They're inverses of each other. So I will not wind up with double time, I will wind up with half time. So A and C are out. And without engaging any kind of equations, I know from Faraday's law, all right, I'm not going to engage an equation, but I will write down Faraday's law, that EMF is negative n, change in flux over change in time. And so if I increase the frequency, then the rate of flux, the change in flux over change in time, that rate is going to increase, which means that I'm going to get a greater induced EMF. So it's not going to be the same EMF, it's going to be a larger EMF, maybe as much as doubled. So the answer is B, half the period and double the peak EMF. 3 more questions. So we're on number 20 of 22. Direct current of 5 amps dissipates a power P, which peak value of the alternating current will dissipate an average power P in the same resistor. Well, if we're talking direct current in an alternating current circuit, the direct current equivalent is not peak, but rather the RMS value. So we're looking at power as relates to current and resistance. So power, of course, is I squared R, and it says the resistor is the same. And so we have average power is I RMS squared times R. So the RMS value is the equivalent of the direct current value set at I RMS is 5 amps. And so if RMS value is peak value over radical 2, then peak value is the RMS value times radical 2. So we have 5 amps times radical 2, or 5 radical 2 amps. That is choice D. 21. Which of the following reduces energy losses in a transformer? So thinner wires. Thinner wires is going to increase the resistance, and I think that's going to lead to higher energy losses. So I'm looking to reduce the energy losses, so thinner wires is not going to do it. Using a solid core instead of a laminated core is going to induce more eddy currents and more back EMFs. A laminated core is better, although I don't know that that fact is necessarily testable. But I would want to use a laminated core instead of a solid core. Iron has more ferromagnetic property than steel does, so I would want to use a core of iron, not steel, and that leaves us with D. If I could get greater flux linkage from the primary to the secondary core, it would reduce energy losses. Then finally, number 22, we have a transformer. And so we have an alternating current on the left side, which means that current is going to vary back and forth in the primary coil, which means that current is going to move in the opposite direction back and forth in the secondary coil. But I too have 2 diodes on either side, so no matter which way the current is going, if it's going positive to negative or negative to positive, it's going to be driving a voltage over to the X side. So the potential difference between X and Y is going to be this guy here, kind of like what you would get from a, I keep on wanting to say voltage divider, diode bridge. And that's it. That's number 22, and that's the last multiple choice, the last paper one for 11-2. Thank you.